All right, everyone. Welcome. Can you hear me okay? All right, great. So, this is the third lecture on the Weil conjectures, and we started by saying that the Weil conjecture is an analog over characteristic P of the Riemann hypothesis. And then we quickly moved on from Riemann hypothesis to formulate the Weil conjecture. So in the first lecture, we did that for the for curves, and in the second lecture for general higher dimensional surfaces, higher dimensional spaces. But to have a bit of fun, I thought for the third lecture, it would be good to revisit the zeta function and talk a little bit about properties of the zeta function in a conceptual way. Okay, so I did a bit of research, and apparently, the first person that seems to have written anything about the zeta function. So the zeta function, the definition is given there: 1 plus 1 over 2 to the s plus 1 over 3 to the s, etc. But the first case people considered was the case s equals to 1. So 1 plus a half plus a third plus a quarter, etc. And there's some evidence that Plato was interested in this sum because of its relations to harmonics. And of course, Plato was interested in music and mathematics, etc. So, but I haven't been able to definitively find out what Plato exactly talked about. But the first person who considered this sum appears to be Nicole Oresme of France, a Middle Ages scholar. And he proved that this sum, 1 plus a half plus a third plus a quarter, etc., diverges. And the proof was actually his proof was the proof that we give to our first-year students. So you group. You take one and then group the next two together, and then the next four, and then the next 8, and so on. And then you observe that a half plus a third, those are bigger than a quarter plus a quarter. And also like a quarter, a fifth, a sixth, and a seventh, they're all bigger than an eighth. So, and you proceed as like this, and you see that the whole sum is bigger than 1 plus a half plus a half plus a half, etc., which diverges. Okay, which goes on to infinity. And this is this was also Oresme's proof. However, his proof was actually lost. So this is Middle Ages we're talking about, and books were being burnt, and who knows what. So his proof was lost and was only found much later. But in the meantime, in the Renaissance era, a philosopher slash mathematician, etc., by the name of Pietro Mingoli, he rediscovered Oresme's result with the same proof, but he didn't have access to Oresme's book or writing. And he also wrote a book about this. You can see the title at the first page of the book, of course, at that time written in Latin. And in this book, he also posed the following problem. So instead of 1 plus a half plus a third plus a quarter, etc., how about we take the squares? So 1 plus a quarter plus a ninth plus 16th, so on. And he wanted to know, can we find a closed form expression for this sum? Can we evaluate this sum? So in the sum notation, this is sum from n equals 1 to infinity of 1 over n squared. Okay. And this was aroused the interest of the Bernoulli brothers. So this was, you know, an amazing sort of family, many of whom were quite interested in maths. And they sort of got onto this problem and helped to popularize it, but they couldn't solve it. They couldn't solve it. However, because of their sort of popularization, Euler became interested in this problem, and he definitively solved it in 1734, finding the sum to be pi squared over 6, which is quite a, even still after 3 centuries, it's still a striking result. Because on that left-hand side, you have a bunch of reciprocals of square. It doesn't seem to have anything to do with pi. On the right-hand side, we get pi squared over 6. And this result actually is the one that brought Euler instant fame. So, and Euler had quite an interesting life as well. He wrote something on the order of 900 mathematical papers. More than a third were written in the last 10 years of his life when he was completely blind. So he would just sort of do everything in his head and dictate it to some other people who wrote it down. And even in the photo of him here, you can see that his eye is a bit crooked. But yeah, he lost his eyesight his last 10 years, but that did not, it seemed to only have helped him in proving theorems. Also, Euler was the first person to discover, to consider, I think the first person, you guys can correct me if I'm wrong, to consider the zeta function. So namely the zeta function as a function defined like the zeta of s being the sum of 1 over n to the s with this, the pi squared over 6 sum being the value of zeta at 2. And Euler proved the following remarkable product formula, that 1 plus 1 over 2 to the s, etc., that zeta has this product expansion, where p in this talk always denotes a prime. Okay? So, and again, this is a very remarkable formula because on the left-hand side, you just have this orderly thing of natural numbers. And on the right-hand side, you have the prime numbers, which are, you know, their distributions is very sort of difficult to understand. And yet, the relationship is governed by this very simple equality. And nowadays, we understand this equality as a reformulation of the fundamental theorem of arithmetic, that every integer has a unique factorization into primes. And combining the Euler product with the with this formula for sum, we get what I call in this talk the Euler identity, which states that the product of 1 minus p to the power minus 2 all raised to minus 1 equals pi squared over 6, which is one of the most beautiful equalities in mathematics, one can argue. And what I want to do, so the first goal of this talk is to give an explanation of this identity, because even after 300 years, it's non-trivial. I bet if you ask like 90% of mathematicians, they wouldn't know how to prove this. It's so let's talk a little bit about how one can think about this. Any questions or comments? Okay, so there's of course many explanations that one can give for this fact, but my favorite explanation comes from what. So I read it in Yuri Manin's Reflection on Arithmetical Physics, which appears in his collected work, which has the nice title of Mathematics as Metaphors. And Yuri Manin, he passed away just this year. He's actually my mathematical grandfather. He was the advisor of Drinfeld, who was my advisor. And here he is with his wife. He was one of the deepest thinkers in mathematics in the past century, first working in Soviet Union and then moving to Max Planck Institute, where he was a director for a couple of decades. So let's have a look at what Manin says in his reflections. So here's an excerpt from Manin's reflections. The physical world as we know it can be described very efficiently by mathematics based on the real numbers, and its further extension, the complex numbers. Recently, it was suggested that at the Planck constant, at the Planck scale, a p-adic topology may become more relevant. This, however, raises a question. Why should one particular p be physically marked? Isn't it more reasonable to believe in a democracy of all available topologies, or at least of all p-adic ones, since R is certainly the first among equals, being defined by the only Archimedean norm? It appears that Euler identity, the one that we just talked about, and a whole series of similar facts can be explained in a way furnishing a very suggestive picture of such a democracy. So that's my goal now, is to provide the explanation, democratic explanation of the Euler identity. Okay, so but to have a democracy, we should have some citizens. So who are the citizens of this democracy? The citizens are ways of measurements or absolute values that we can put on the rational numbers. So what is an absolute value? Well, absolute value is a map which is always positive and is 0 if and only if x is 0. And the product of absolute value is the absolute value of product, and the sum of absolute value is greater than or equal to the absolute value of the sum, the triangle inequality. And of course, the definition is modeled on the usual absolute value, the usual way of absolute value on R, which I sometimes denote by the absolute value sub infinity. Now, so we call this sometimes the infinity norm. Why? If you have been in these lectures before, the reason is we think of this norm as being the prime at infinity, because you should think in the function field case, we had this A1, and we saw that the completion of A1 is P1, is the point at infinity, is the completion at of A1. So this is the point at infinity, so to speak.
So
yes.
I interrupt.
Yes.
Is there any chance you can make that bigger?
Can you zoom in?
It's very hard to read from the room.
Okay, let me see. There should be.
I don't think there was
How's
very
that?
large borders on the left and right.
How's
Great.
that? Is that better?
Yeah, that's much better.
Sorry. Thanks for stopping me. Yeah, when the writing becomes a bit dense, it's becomes maybe a bit. Okay. Is that good? Okay, excellent. All right, so an absolute value. So you haven't missed anything if you couldn't read before. There wasn't much writing. And now there's a bit of writing, so it's good that you warned me about this. So that's an absolute value. Now, the point is that aside from the usual absolute value, we have a whole bunch of other absolute values. And these are given as follows. For each prime p, we define the p-adic absolute value to be 0 if x is 0, and otherwise p to the minus n, where p to the n is the biggest factor of p dividing our rational number. Okay, and exercise, check that this satisfies the definition. It's a norm, it's an absolute value. And each absolute value gives rise to a different topology on Q. These are all different topologies, and this is what Manin was talking about, democracy of topologies. So now we have the following theorem of Ostrowski, that every absolute value on Q is equivalent to one of these absolute values. And another part of it is that none of these are equivalent to each other. Okay, so they all give different topologies. So if we complete with respect to the usual absolute value, then of course we get the real numbers. This is one of the constructions of the real numbers, the Cauchy construction. You complete with respect to the Archimedean absolute value or the infinity norm. If we complete with respect to the p-adic norm, then we get something that's called p-adic numbers. So I just want to talk briefly about p-adic numbers, because democracy means that we should talk about all of them at once. There's a question on the chat. Who first defined the p-adic norm? Very good question. I actually don't know. If somebody knows, please let me know. Probably a quick Google search might tell you.
I would say that like a lot of the historical development of the p-adic numbers is probably attributed to Hensel. That's probably one name that I would say is very important in the history of the p-adic numbers. I'm not sure who first wrote down the p-adic absolute value though.
Right, and probably Hensel came after Ostrowski. So I'm not sure actually. I'm not sure. Good question. There's plenty of historical interest which you can follow up on. Okay. So let's keep going. I want to tell you just a bit about p-adic numbers, just to make sure you're not scared. So now I've lost control of the. Okay. So p-adic number is by definition the completion of Q with respect to the p-adic norm, and I write the completion like this. This is the usual notation for completion. Okay, just as every real number has a decimal expansion, every p-adic number also has a decimal expansion, and it looks like this. Instead of, well, of course, not in base 10, but in a base p, so to speak. So, and it looks like this. It's of the form p to the n times a0 plus a1p plus a2p squared, dot, 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 where ai is 0, 1 to p minus 1. Now, the only thing you have to be careful is addition and multiplication in this ring are a bit funny, but I don't want to get into it right now. And x is in Q if and only if the expansion is finite. So exactly like the real numbers. And I also want to define the p-adic integers to be the ones where you start with a0 plus a1p. I should say here that a0 is non-zero. Okay. So the integers are the ones that that have a p-adic norm equal to 1. Because the p-adic norm of these numbers, so of course the p-adic norm extends to p-adic numbers, because just as the Archimedean norm extends from Q to R, the p-adic norm extends from Q to QP, and the integers are exactly the ones of p-adic norm 1. Alternatively, you can think of them as the completion of Z with respect to this norm. You can complete rings, not just fields. There was a comment.
I should just jump in quickly as well on the decimal expansion thing. It's not quite true that it's in Q if and only if it's finite. Same with real numbers. You can have infinite decimal expansions of rational numbers.
Right.
So for instance,
what's the
like
right
in the
word to say?
For instance, the 2a, like 1 plus 2 plus 4 plus 8. If you just have 1 as your coefficient everywhere, you get -1. That's the same as -1 in the 2-adics. Is it repeat? I have to think about it for a moment. It might be if there's some sort of periodicity, but there might be
just like the real number. Okay, so I failed my first year analysis.
Yeah.
Yes, so of course this is false. So well, one direction is true, but not the other direction. And probably the answer is more like periodicity, like in the real number. But I'm sure it's not too hard to figure out when it's actually a rational number. Thanks a lot, Angus. Yes, any other obvious mistakes? By the way, Drinfield always told me that when writing the paper, your goal should be to hide your mistakes as much as possible. That was a quote from him. His idea was that you can never have no mistakes, but you should hide your mistakes. But in this case, I clearly failed in hiding my ignorance. Okay, or rather forgetting something that I knew up until last semester when I taught the course. All right, so now we're going to bring all of these different topologies into a voting assembly. And the voting assembly has a name called Adels. So before Adele became a pop star, it was a name for different topologies on Q. And the definition is that you take a product of R together with all the p-adic completions. Now, this product, there's a prime there because actually it's not just a free product, but we assume that all by finally many places, the p-adic numbers are p-adic integers, but forget about that. It's not that important. The point is that we take a product of all the completions, okay? And we have an embedding from Q inside each of the QPs and inside R, and that gives an embedding from Q inside the Adeles, okay? So the Adeles are the voting assembly for us. Any questions about this page before I move on? Okay. So, okay, now let's see democracy in action. So namely, let's sketch a proof of this Euler identity that pi squared over 6 times the product over prime of 1 minus p to the minus 2 equals to 1. Okay. So the idea is as follows, and if you don't know the words in this, forget it. You can go to sleep for this page and then come back after. But the idea of the proof is as follows. The left invariant form on SL2 and the p-adic norm together produce for you a measure on SL2QP. Well, okay, unique up to something, but let's not worry about that. Just like the fact that you have a measure on SL2R, which comes from the left invariant form on SL2R and the Lebesgue measure. Okay, so there's a p-adic analog of that. And if you take the product of these measures, then we get a measure on the adelic points of SL2. Of course, I can have SL2 with entries in any ring, so I put the entries in Adeles. So, okay, now I'm going to normalize this measure so that when I mod out SL2 by A by SL2Q, my measure is 1. Now, there's something not trivial here. One has to know somehow that this has finite volume, okay? But let's believe that. This is supposed to be a sketch. You can fill in the details. Okay, so we normalize our measure to get volume 1 on this quotient. And now we're going to compute the volume component-wise. Remember, the Adeles are a product over all the topologies, over all the completions. So this SL2A divided by SL2Q, one can show, also has a product expansion. Namely, it's SL2R divided by SL2Z modulo product of SL2ZP. Okay. So now we compute the volume component-wise. Now, the volume of the p-adic part is actually very easy to compute. That you can compute, and is exactly what we want, is 1 minus p to the minus 2 with this normalization of the measure. So that's an easy, actually, computation. Computing the volume of SL2R divided by SL2Z is a bit more involved, but that's also a very interesting story. So the answer is pi squared over 6. And how do you go about computing this? To start, notice that SL2R acts on the upper half plane. And the stabilizer of I is SO2R, so the circle. So the SL2R modulo SO2R has a fundamental domain, which is the upper half plane. Now, this has infinite volume, but when you go from SO2R to SL2Z, then it becomes a finite volume thing, and you can construct the fundamental domain for it and compute explicitly what is the volume of that fundamental domain, and that volume is exactly pi squared over 6. And so therefore, what we find is that 1 equals pi squared over 6 times 1 minus p to the -2, the product over all p's. And this is the democratic proof of the Euler identity. Any questions about this?
Maybe
That's
just,
Yes.
sorry.
Go ahead, go ahead.
I was just going to say, I think if you compute the measure of the modular curve, it's not usually pi squared unsexed unless you're using your normalization for the Haar measure. Like I think if you do the standard computation, it ends up being something like pi on 3.
Right. So here, I guess, yeah. So one has to be careful about what this condition means on each of the local factors. Does that make sense? So it might not give the standard measure. It might give a different normalization than the standard, or the one that people usually use. Does that make sense, Joe? Was that Joe?
Yeah, it was. Yeah. And it does. Yes.
Ramiro had a question.
Yeah, I was wondering if you do the same game with SLN, do you get some formula for the p to the n? I mean, for the other.
No, I don't think you get formulas for other values of zeta function this way. But the story for SLN is, of course, also very interesting. So this whole story goes under the name of. So when I saw this proof, I thought, okay, this is great. I should get an honor student to do this properly and write out the details, and also generalization to SLN and other reductive group. And so my student Tuan Pham wrote an honors thesis about this. And this story goes under the name of the Tamagawa numbers, which, by the way, so Weil, under Weil, the same Weil as Weil conjecture, had another set of famous conjectures, which are called his conjectures on Tamagawa numbers. So Tuan wrote a thesis about, honors thesis about Weil's conjecture on Tamagawa numbers. And this whole computation can be rephrased as saying that the Tamagawa number of SL2 equals 1. And Weil conjectured that the Tamagawa number of every simply connected semisimple group is 1. But let's not go there, because that's not the goal of this talk. But if you're interested, you can go and read Tuan's thesis. Any other questions or comments? Okay. Yeah, I was totally blown away when I first saw this proof. I really liked it. So let's read what else Monin says in his memoir. So Monin continues, with some strain, one can generalize and state the following principle, which is the main conjecture of this talk. On the fundamental level, our world is neither real nor p-adic. It is adelic. For some reason, reflecting the physical nature of our kind of living matter, example, the fact that we are built of massive particles, we tend to project the adelic picture onto its real side. We can equally well spiritually project it upon its non-Archimedean side and calculate most important things arithmetically. So I leave you with that spiritual advice, but let me just say what that means in terms of the proof that we just did. So this pi squared over 2, that's the real part, and this product is the p-adic part, and the whole thing is the adelic thing. Okay, so that's how they fit together, these different measurements. Okay. So next, I want to come to Riemann. And so Riemann was the first person to consider the zeta function as a function of complex variable, not real variable. And he was Riemann was an amazing mathematician. The more I sort of spend time in mathematics, the more amazing his stature becomes. So for me, he is the greatest. And here's a list of papers published in Riemann's life. So these are papers that he published himself. and there is a grand total of 11 papers, which if you add the number of pages is probably something like 300 pages. And these are probably the most consequential 300 pages in mathematics. There is probably there is a bunch of other papers of his that were published afterwards. He didn't want to publish them. He didn't publish them, but Dedekind and Weber and other people that were poring over his results published them posthumously. So there's equal number of papers under his name that are published after his death, and a whole bunch of his writings got lost because the cleaning lady apparently chucked them out after his death. So we don't know what other gems was in them. But here's a quote that I really love from Dustin Clausen. All we do is but a candle to Riemann's light. So that's really, I feel, is true. I learned this quote from Jordy Williamson. Okay, so let's talk a little bit about what Riemann did. Okay. So first thing Riemann did was analytic continuation. Namely, he proved that the zeta function has analytic continuation to all complex numbers except one. Okay, what is a conceptual explanation of this fact? Also, I looked around on the internet, and here's my favorite one, of course, from our favorite current mathematician, Terry Tao. So Terry Tao says, just take the continuous version. Okay, so instead of the finite sum, take the continuous interval version, which you take the integral from 1 to infinity, instead of taking the sum n equals 1 to infinity. And this integral, you evaluate it, and you get 1 over s minus 1. So you immediately see that, well, the integral has meromorphic extension with a simple pole at s equals to 1. I think that's the first order of approximation. This is a great explanation for why we expect the Riemann zeta function also to have this property. I wish somebody told me this 20 years ago, 25 years ago, but they didn't. I had to, prepare for this talk to learn this explanation. But it's sort of an obvious thing after the fact. You just look at the continuous version, and it's clear what one should expect. Okay, and the rest is analysis. Go analyze, right? I mean, okay, if you don't like analysis, close your eyes for 5 minutes. But the analysis is also not terrible. So it's sufficient to analyze the residual, right? So we have the continuous, and we subtract, there should be n equals 1 to infinity, the discrete, and we have to analyze this term and show that it continues, analytically continues. So we have a Riemann sum type, the Riemann type sum, of the kinds that we write for our first-year students, which hopefully I copied correctly from Terry Tao's explanations on Math Overflow. So then, therefore, one can rewrite, using this Riemann sum, one can rewrite the residual as a sum like this. And this is now big O of 1 over n to the real part of s plus 1. And so if from this fact, you can easily see that you can analytically continue to real part of s bigger than 0. So we already pushed the line from real part of s equals to 1 to real part of s bigger than 0. And Terry Tao explains how you can push the line all the way to real part of s bigger than -1, bigger than -2, and inductively get your analytic continuation. Okay. So, or alternatively, once you've pushed it to real part of s bigger than 0, then you can use the functional equation, which I will talk about in a minute. Okay. So I find this a very satisfying explanation of the analytic continuation of the Riemann zeta function. Any questions about that? Okay. So go and read Terry Tao's. There's other, by the way, on the same post, there's people gave other explanations of this analytic continuation. And somebody else's explanation got more upvote than Terry Tao's, which was surprising, but I liked his explanation more. I recommend you go and have a look at the other ones as well. Okay. So next, I want to talk about the functional equation. So this is the functional equation is zeta of s is almost equal to zeta of 1 minus s. Almost, okay? And I will explain what I mean by almost. And here's a democratic explanation, which I will just give you what Terry Tao says on his blog, and then I will explain. Okay, I mean, his blog post is many pages. I show you the first page of the blog post. So he says this is a different post of Terry Tao, by the way. So there are many proofs known of the functional equation. One of them, dating back to Riemann himself, relies on the Poisson summation formula, blah, blah, blah. And then he says, applying the formula to the Gaussian, which is its own Fourier transform, and then applying Mellin transform, one suit obtains the functional equation. But then he goes on to say, in his famous thesis, Tate reinterpreted the above argument using the language of Adels, so the democratic language. And then he says, in this post, I will write down both Riemann's proof and Tate's proof together to emphasize the fact that they are, in some sense, the same proof. However, Tate's proof gives a high-level clarity to the situation, in particular explaining why the gamma factor at infinity fits seamlessly into the Riemann zeta function, and furthermore allows one to generalize the functional equation to other settings and other L functions. So Terry Tao is also in favor of the democracy in action. So now what I want to do is talk a little bit about Tate's and Tao explanation and Tate's thesis and Tao's explanation of it. Okay. So this font might be familiar to you from Terry Tao's blog, if you spend some time on his blog. Okay. So the trouble with the Riemann zeta function is that its definition violates democracy. More precisely, what it does is what is called tyranny of majority. Why? Because let's look at the one definition of the zeta function, which is given in terms of the product expansion. Now, this definition, we have majority of the norms, but not the most important norm, which is the Archimedean norm. So the usual absolute value playing no role here. Okay, so this is what I mean by tyranny of majority. We have all but one of the absolute values, but what the zeta function is missing is the contribution from the Archimedean place, from the Archimedean norm. Okay. And to get the most natural form of the functional equation, we have to restore democracy by giving R its due. Okay, so that's sort of that's going to be the slogan, and we will see. So we have to multiply this function by something, and as Terry Tao mentioned, this something has to do with the most important function in maths, which is arguably the Gaussian. Okay, so it's quite remarkable that the Gaussian also comes into play when dealing with the Riemann zeta function. By the way, I asked the AI to draw a picture for the talk today, and I gave the AI democracy and the zeta function, and the answers were nonsensical. So I mean, the pictures that it drew for me were terrible. Then I gave the AI the tyranny of majority, and that one it did better. So here's the picture of AI of tyranny. Oops, of tyranny of majority. Here it is. So here's what AI wrote. AI drew. I had to try a few different actually AIs to get a reasonable picture, but here's AI's depiction of tyranny of majority. It's much better than when I gave it the title democracy and zeta function. That one really screwed it up. Okay. All right, so let's restore democracy. Before that, I need to do a bit of review of some fundamental concepts in mathematics. So first of all, the Fourier transform. So suppose I have a function. This Fourier transform is defined by the integral of e to the minus tx f of x dx. And okay, let's not worry about convergence. Take your function to be a, I don't know, Schwartz function, whatever, so that this Fourier transform is also a function. Otherwise, it would be a distribution. Anyway, now Fourier transform has a multiplicative version, which is called the Mellin transform. And this is by you take the integral, not over r, but over r star, and you take x to the s f of x dx. And this is called the multiplicative Fourier transform because it's, well, the group structure that we're using is the multiplicative group of r star instead of the additive group of r. And also, if you think about it, this e to the tx, this is a character, additive character of r, and x to the s is a multiplicative character of r star. So that's what's going on. We're doing one-dimensional representation theory, if you wish. I think it should be s minus 1. Maybe my normalization is not correct. S minus 1. Okay. So,
Masood, the reason you want it is because you want the Haar measure for the multiplicative reals, and that's dx over s. Oh, sorry, dx over x.
okay. So, well, okay, but so I could also, if I define dx to be the right measure, then this is correct, right? Depends on, I guess, what we mean by dx. But yes, I agree.
Sure.
Great. Some people, not me, actually understand measures. So thank you, Joe. Other questions or comments? All right, so now let's define the Gaussian. The Gaussian, I'm going to use this normalization, is e to the minus pi x squared. And this is, of course, one of the most fundamental objects in mathematics. I mean, if you were, say, in applied math, maybe you don't care about the Riemann zeta function, but you definitely care about the Gaussian, or if you're an engineer, etc. All right, and exercise is that the Gaussian is actually invariant under the Fourier transform. So this is a fixed point under the Fourier transform. So hopefully I have the correct normalization for this to be true. Okay, and now we define the gamma function to be the Mellin transform of the e to the minus x. Okay, so that's definition of gamma function. And I have an exercise for you that gamma of n equals n factorial for all integers n, positive integers n. So in other words, gamma is analytic continuation of the n factorial to complex numbers. Okay. All right. And what we're going to do, so the function that we're going to add to the zeta function to complete it is going to be not gamma, not the Mellin transform of e to the minus x, but the Mellin transform of the Gaussian. So that's exactly the right thing to add to the Riemann zeta function to get the completed, the correct function, so to speak. So let's democracy restored. So we define the consider the Mellin transform of the Gaussian. And exercise for you is that this is actually pi of to the power minus s over 2 times gamma s over 2, where gamma was defined to be the Mellin transform of e to the minus x. Okay. This exercise is so that you just recognize the Mellin transform as Gaussian as really the factor at infinity of the zeta function. Okay, so the completed zeta function is now defined to be the product of the Mellin transform of the Gaussian with the usual zeta function. And here is now the democracy in action. So every absolute value on Q is represented. And this is sort of the correct object for studying functional equations, etc. This is the right thing. Of course, the original zeta function has the advantage of being defined in terms of 1 plus, 1 over 2 to the s, blah, 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 a definition that you can give a child. But this is really the right function, so to speak. And just a remark that if we define the p-adic Gaussian to just be the characteristic function of Zp, then in fact, the Mellin transform of the p-adic Gaussian becomes 1 minus p to the minus s to minus 1. And so therefore, what the completed zeta function is by definition the Mellin transform of the adelic Gaussian. So that's the slogan of this talk, if you want. The zeta function, the completed zeta function, is the Mellin transform of the adelic Gaussian. Okay, but that's an aside. Any questions about this?
Can you explain why that's a natural definition?
Yes,
the,
actually, good question. I asked the exact thing on Terry Tao's blog. So that's what he says in his blog. Terry says that 1 over Zp, somehow we put the Gaussian to be 1 over Zp. And then I posted the question. I said, why is that a right Gaussian? So my question was, I prefer to see a general definition of a Gaussian for a local field, which then specializes to 1 over Zp for p-adics and the usual Gaussian for R. Actually, I haven't checked if anybody answered that question or if Terry Tao answered. So very good question. And I hope that he answers at some point. And maybe the answer was obvious to everybody else on his blog, but nobody else asked it. Other questions or comments? Okay. So the functional equation, sorry, the functional equation is z of s equal to z of minus s. So what that does means that our zeta function on this side of the line should look the same as on that side of the line. Okay, and this is a very clean formulation of the functional equation. You see, if you just try to do it with the zeta without completion, it would be a mess with all the pi's and the gammas, etc. This is sort of the right way to state it, and as Terry Tao explains, also the right way to prove it. So the proof follows from Poisson summation, which and there's a version of Poisson summation formula also for the adelic points, and that gives you a satisfying explanation of this identity. But I don't want to sort of get into details of that. I invite you to have a look at his blog post. Okay, so I want to end. So this lecture we're going to end a bit earlier. So I want to end by an exercise. So use the functional equation and the Euler identity, the identity of sum of 1 over n squared equals pi squared over 6. You see from those two very quickly that zeta of -1 has to be -1 over 12. Because you see, -1 and 2, the midpoint between -1 and 2 is exactly, well, let me not say more. So anyway, you can sort of derive this. Yeah, so if you have -1, okay, so what that tells you is that, so what you recover is the Ramanujan sum, that 1 plus 2 plus 3 plus 4 equals -1 over 12, which of course makes no sense, but the meaning of it is comes through from this is value of zeta at -1. So that's the regularization that we just performed gives the value -1 over 12, which is a source of endless entertainment for people. Okay. that's all I wanted to say. Thank you very much for your attention. And next week, I think we have Angus, who's going to tell us. So we're going to go back to Weil conjectures next week. And Angus is going to tell us about the elliptic curve case. So we're going to do a particular case of Weil conjectures that was discovered actually more than 100 years ago. All right. And I'm happy to answer any questions.
May I ask something, Masoud?
Sure.
So you gave us a way to prove the identity of the sum of n over n squared equals p squared over 6 by considering this adelic identity, taking measures.
Yes.
What is peculiar to s equals 2 here? Can you do the same kind of proof to get other?
Well, that's what Ramiro was saying. Honestly, I haven't checked. Like he was saying, like, can we consider the SLN case and recover Euler's formula for zeta of 2k in terms of Bernoulli numbers? Yeah, I don't know if we can get that from SLN. I don't know. Yeah, I haven't thought about it. I haven't thought about a democratic proof of the other ones.
But for odd s, this.
Well, odd s, yeah, good luck. It's yeah.
So Masoud, about your question on the Terry-Tau law, so a conjecture answer could be related to the Fourier transform on p-adic numbers, right?
Yeah. So obviously,
And of course, this is a fixed point.
If the Gaussian was the unique fixed point, then that would answer my question. But the problem is that the Fourier transform has many other fixed points. So the real Fourier transform, right? So I wanted, I actually Googled this, and there was a Math Overflow post which gives a bunch of different fixed points for the Fourier transform aside from the Gaussian. So we need another characterizing property of the Gaussian. Yeah, so being the fixed point of the Fourier transform is not characterizing. And I don't know how one characterizes Gaussian. Actually, that's an independently good question. What's the characterization of the Gaussian?
It's self-derivative.
Yes, self-derivative. I mean, not quite, right? You get a factor of x, right? That's not
Exponential.
That would be e to the x is self-derivative. That's, yeah. Oh, but maybe the functional equation that it satisfies. So f prime equals x times f. Yeah. So yeah, of course, the functional equation would determine it, I guess, uniquely, and maybe such thing makes sense adelically also. It comes up in central limit theorem. Yes. Is there a p-adic central limit theorem? I don't know. Yeah.
Also, I wanted to remark this. In the last formula you gave us, you said like you should look at the functional equation as a Mellin transform of the adelic Gaussian, but there's a big discrepancy, because for the reals you look at the Mellin transform of the Gaussian, and for the p-adic integers you look at the Mellin transform of the identity over ZP.
Well, that's what we're debating, right? The claim is, Terry-Tau is claiming that the identity is the right definition of the identity, the characteristic function of ZP, more precisely, is the right definition of the Gaussian.
Okay, sorry, I missed that.
So that's exactly the point. Why is it the right definition? Conceptually, I haven't found a good answer to that. But that's sort of what Terry-Tau is saying. At least that's my reading of his blog. Okay, there's a chat question. Is there a historical evidence that it was lost because of deliberate suppression, or rather as an accident? I don't know. I don't know. Good historical question. I don't know why it was lost. But clearly, the fact that science and books in general were not so valued in the Middle Ages had something to do with it, right? Because since the Renaissance, we haven't lost anything, right? But at least I would hope so. But certainly, there's plenty of things that were lost in Dark Ages, Middle Ages. So, you know, if the only book that you cared about was the book, then other things getting lost is perhaps not surprising, whether intentional or not. All right. Other questions or comments? All right, everyone. Thanks for being here, and we'll see you next week. Bye-bye.
Thank you.